Hey folks, we're live now. So we'll be solving practice session 3 today and just waiting for other people to join in. Let's give a couple of minutes. We're also sending an SMS to all the registered students so that they can come and join us. So just give us a couple of minutes. We're good? Okay, so just informed everyone to join. Just give me a second here. Okay, sounds good. Let me just check if everything is all right. I hope I'm audible. Guys, can you please check if I'm audible?
It's good. Audible is coming right? Yes.
I'm audible, right? Perfect. Okay, sounds good. So, hey folks, I think the audio is also clear. We were just cross-checking that. Okay, let's wait for a couple of minutes before we get started, and then we'll dive into each of the problems. We have slightly more problems this time. That's why I wanted to get started. We have, I think, 19 or 20 problems today. So it might take us a little more time than every day to finish off everything. So let's just wait for everyone to join in. And hey, folks, we have a few folks who already joined in. Hey, folks, good evening, and thank you for joining again. So, while others join, we have a couple of minutes. So if you want me to discuss anything, if I know the topic, I'll surely discuss it. So let's give everyone a couple of minutes, and then we'll jump into it. Hey, good evening, folks. I see a few comments popping in here. And just waiting. Just give us a couple of minutes. We'll start at 7:04 sharp. It's 7 IST. Yeah, I keep saying IST because we have some students, not for the GATE course, but for the AI course, who join in different time zones across the world. So I have to make sure that I tell the time zone because there are people joining from almost all the major time zones on Earth. So yeah. Okay, folks, a couple of more minutes. In the meantime, let's just talk about, I think the objective today was to finish all of the sorting algorithms. And the assignment is also slightly lengthier. Intentionally, we gave more content, as all of you know. We gave slightly more content this time around. Some students reached out to us and they said they couldn't finish all the content or they couldn't finish the practice problems. So after discussing with all of our students, we thought for this time only, we will extend the deadline a little more. So till this Saturday, we'll give them time to finish all of the sorting algorithms, all of the asymptotic analysis, everything. And so that next week we can get started at a faster pace. As I informed earlier, as time progresses, we need to speed up. In the first week, we were going at a slightly slower pace. But if we want to finish all of the subjects fast and have enough time for practice and for mock tests and things like that, we should try and finish more content. So I understand this is just the second week for some of you, but let's get warmed up. We have had enough time for warm up. From next week, we will not be making these extensions. Only for this time, we are extending the deadline to finish all of the content up to end of sorting. Instead of today, which is a Wednesday, we'll extend it up to Saturday, right? So you have time till Saturday to finish all the content, all the practice tests. Of course, we won't just let you off the hook. We will send 30 practice questions by tomorrow end of day. And these practice questions will be from the starting of the whole data structures algorithms course up to the end of sorting, right? Including asymptotic analysis, recurrence relations, master theorem, all the sorting algorithms. We'll discuss all of that. So these 30 problems, we are just setting these questions up. We'll send it to you by tomorrow end of day as practice test 4. We will discuss these 30 questions in the Saturday session. And from next Monday onwards, we'll go at full throttle. Of course, you'll have to start spending more time on the course because we want you to finish the course. We want to finish all of the content as fast as possible. Of course, while practicing and revising regularly so that you don't forget what you learned a few weeks back. Okay. So only this time we are making this exception. Hopefully, all of you are on track. All of you will move fast because you have the weekend also, Saturday, Sunday, to finish everything. So please try and finish everything. By next Monday, we are going to start some of the data structures, right? Basic data structures like stacks, arrays, queues, search tree or binary search trees, graphs, typical trees, all of that will start from next week. Okay. Okay, folks. Okay, sounds good. So let's get started with this. I'll move to the questions interface. Take myself off the screen. Okay, sounds good. Where are we? Yes, we are here. Okay, so let's go in here and start solving the problems one by one. Of course, your order of questions may be different from mine, so please bear with that. Okay, let's go one by one and see this. Okay, some of these questions are straightforward and simple, right? I just solved some of these questions, almost all of these questions in the evening, and I think I finished all of them in like 35-40 minutes. So some of them are very straightforward. There are a couple of tricky ones, but our team also told us a few shortcuts which I couldn't figure out. Anyway, so you have selection sort and quicksort. So the question here is that you have selection sort and quicksort. Both of them fall in the same category of sorting algorithms. What is this category? Very simple question. Are both of them order of n log n sorts? No, no. Selection sort is certainly not order of n log n. Without doubt, it's not n log n. Selection sort is obviously order of n square algorithm, right? And quicksort, if it's not a randomized quicksort, in the worst case, could take order of n square. So option 1 is certainly not true. Are they divide and conquer sorts? Or in other words, are they recursive? Of course, quicksort is recursive, but selection sort is not. Because in selection sort, we are picking one element after the other, right? The smallest element, the second smallest element, etc., and then filling it in. So it's certainly not a recursive algorithm. Are they both comparison-based sorts? Yes, they both are comparison-based sorts, obviously, right? Because both of them compare numbers, right? Both of them basically compare numbers or compare values that you have. Unlike your count sort, think about your count sort or radix sort, variation of count sort. These are non-comparison sorting algorithms. So option C is certainly one possibility, but also let's look at option 4. Average time is quadratic. No, for quicksort, the average time is order of n log n, right? The average time for quicksort is n log n, right? For selection sort is obviously order of n squared. So the right option here is C, right? So very straightforward question, nothing hard, nothing rocket science here. Okay, so what's the second question now? Let's go to second question. What is the question here? Suppose we are sorting an array of 8 integers using quicksort. One thing you might notice is I keep underlining all the key terms in the question. That's a good habit in general, so that you don't miss out any key aspect later on. And we have just finished the first partitioning. We have finished the first partitioning with the array looking like this, right? This is how my array looks like this after the first partitioning. Which element is correct? Okay, so let's read the options. Which statement is correct, right? The pivot could be either 61, 71. Pivot could be 61, but not 71. Pivot could be 71, but not 61. Neither 61 nor 71 could be pivot. First, let's see, can 61 be pivot? Okay, what does the meaning of pivot? So once I've moved my pivot, at the end of first partitioning, what happens? The pivot element that I've picked comes to its final location. All the elements to the left of it should be less than the pivot element. All the elements to the right of it should be greater than that. Right? In this case, 34, 12, 56, 21, all of them are less than 61. All of them are less than equal to 61. And all the elements here are greater than equal to 61. So 61 could be a pivot element, right? 61 could have been a pivot element without doubt, right? Makes sense. What about 71? Now let's look at 71, right? If 71 is a pivot, all the elements all these elements to the left of it should be less than 71. All the elements here should be greater than 71. That's not the case because this element is less than 71 and this element is greater than 71. So 71 cannot be a pivot, right? So the right answer here is the pivot could be 61, but not 71. Obviously, very simple. This is just help. I mean, these questions are straightforward, right? If you understood what partitioning means and what's happening at the end of first partitioning, and if you understood the quicksort algorithm, these questions are simply straightforward, right? So let's go to the third question now. Some of these are easy questions without doubt, right? Okay, so this is a tricky question because I got confused when I was solving this. Okay, the minimum number of comparisons required to sort 5 elements. Okay, the word here is minimum and comparisons. Now, I could argue, of course, there is some confusion in the question. The question is not perfectly framed. That's because imagine if I have 5 numbers like this. Imagine if I have 5 numbers which are already sorted. How many comparisons do I need to ensure that I mean, imagine if I'm given this already sorted array. How many comparisons I'm going to make? I'm going to make one comparison, right? I'm going to make second comparison, third comparison, and four comparisons. So I can actually, I mean, if my array is sorted, because nothing about the sortedness of the array is mentioned here. So the minimum number of comparisons required to sort 5 elements, if it is already sorted, is only 4 comparisons, right? So the question could have been said, the minimum number of comparisons required to sort an unsorted array, an unsorted array of 5 elements. Okay, that's important. To sort an unsorted array of 5 elements is a better framing of the question, or else all the 4 answers here are incorrect, right? So imagine we are given an unsorted array with 5 elements, right? Then we already seen in the course videos that any comparison sorting algorithm, if you take any comparison sorting algorithm, the minimum number of comparisons you need is, suppose if you have n elements, right? We have shown this, right? You need log n factorial. I'll again explain this briefly here. You need log n factorial seal of this. These are the number of comparisons you need. Again, we derived this whole thing in the course videos. And one way to derive this, one simple way to derive this is, if you have n numbers, right? You have n factorial permutations of the numbers, right? You have n factorial permutations. And to reach these to accommodate for all of these n factorial permutations, if you draw a comparison tree that we discussed in lots of detail in the course videos, the depth of this tree will be log n factorial seal of that, right? And at each node in this tree, you're going to make a comparison, right? In each node of this tree, you're going to make one comparison. So the minimum number of comparisons that you would need will be log n factorial seal, right? Again, I've not gone into full depth on how we got log n factorial seal here, because we've already discussed this in course videos in a very nice 30-minute video explaining this and deriving it step by step. So given that we know that comparison sorting algorithms need log n factorial seal, right? Again, I don't have to remember this by heart. If you remember the proof, you can actually come to this very quickly. Okay, having said that, what is n? N is 5 now. So if this is log 120, right? Seal of this. 5 factorial is 120, right? So what is log 120 seal? If you just solve it using the calculator, you will get a value of 7. Right? Very simple. Of course, this is log base 2. Okay, even without a calculator, you can do it, because 2 power 7 is 128, 2 power 6 is 64, 2 power 8 is 256, right? Which means the log of this will be between 6 and 7, because this value here is 120, right? So the log of this will be between 6, it will be some 6 point something, very close to 7. The seal of that is obviously 7, right? Because this is log base 2, because what we have is a binary comparison tree. So the right answer here is 7. Very good question. Small modification would have been a terrific question. Okay, sounds good. So let's go to the 4th question now. What does the 4th question say? Okay, so the 4th question says, let A be a sequence of 8 distinct integers. Distinct is important. 8 distinct integers sorted in ascending order, right? We already have them in ascending order. Okay, so A is basically 8 numbers in ascending order. Very good. How many distinct pairs, again, how many distinct pairs of sequences B and C are there such that, so you're given 8 numbers, A0, A1, okay, let's not use 0 indexing, let's just use indexing 1, A1, A2, so on and so forth, A8. All these numbers are distinct. They're already in ascending order. Very good. Now you want to break this up. So this is, let's say, your array A. You want to construct array B and array C. Okay, in such a way that each of them is in sorted order. Okay, B has to be in sorted order, C has to be in sorted order. Okay, B has 5 elements, 1, 2, 3, 4, 5. B should have 5 elements and C should have 3 elements. Okay, very good. The result of merging B and C gives A. Oh, okay, good. So which means I have to use only these elements. Basically the question is, given these 8 elements, which are distinct and which are in ascending order, in how many ways can I construct arrays B and C such that B contains 5 elements, C contains 6 elements. These 2 arrays are also sorted, which means the order here should be same as the order here, right? And all the numbers in both of them should be these numbers only. And When I merge them, I should get this, which means each number will be either in B or in C, right? That's what it is. This is very simple, right? Let's look at it. First, let's try to fill C, because once I fill C, rest of the elements will go to B, right? Because you need to have B union C equals to A, right? If you think about these as sets, this needs to be satisfied, and B intersection C should be equal to null, right? Otherwise, by merging both of them, you don't get it. Otherwise, you won't satisfy 3, right? So basically, I have to fill 3 elements here by picking from these, such that suppose if I pick A2, let's assume I place A2 here. I can't place A1 here. I have to place some other element from this list, right? So this is simple combinatorics, right? This is something that you learned in your 10th or 11th or 12th class, right? I have 8 numbers. Okay, I can choose any 3 numbers out of this. Pick any 3 numbers. Okay, pick any 3 numbers from this and place the smallest number here, the second smallest number here, the third smallest number here. That's it. So the answer is 8 choose 3, 8C3. Pick any 3 numbers from here. See, this question has been made to look complex. It's actually a simple question. Okay, it's actually a simple question. People have made it like, people have made a big gungo about it, made it look complex. This is about picking 3 numbers from this 8 numbers. Place the smallest number here, second smallest number here, third smallest number here. There are 5 more elements left. Place those 5 also in B. See, once you've picked this, you're left with 5 more elements. Also place them here. Because once you want to place them here, there is only a fixed ordering. Because these numbers are already ordered in ascending order, right? So the answer here is 8 choose 3. What is 8C3? It is 8 into 7 into 6 by 3 into 2 into 1. Right? This is 8 choose 3, right? Nothing but 8 factorial by 5 factorial into 3 factorial. That's what it is, right? 6 gets cancelled, 7 8s are 56. 56 is the answer. Okay, while this question looks crazy, it's actually a very simple problem. Okay, so this is 4th question. So let's go to the 5th question. Okay, so the 5th question here is identify the sorting algorithm that only uses comparison between elements to determine the sorted order. Okay, so basically he's asking which of these algorithms are comparison based sorting. Counting sort is not, radix sort is not, they both are not. Obviously neither counting nor radix sort is comparison based. Obvious. This is like trivial. 10 seconds you should be able to answer this question. Read the question carefully and answer it. That's it. Okay, this is an interesting point. Okay, so consider a list of recursive algorithms and a list of recurrence relations as shown below. Okay, there are a bunch of recursive algorithms and recurrence relation. Each recurrence relation corresponds to exactly one algorithm and is used to derive the time complexity of the algorithm. Very nice. So it is given some 4 of them. Here there is something called as towers of Hanoi. I haven't covered this because I wanted to cover it a little later in the course. But don't worry, even without this, you can solve this question. Okay, but I'll cover towers of Hanoi, which is a very standard problem which is used in most textbooks to introduce recurrence relations or recursion itself. I'll cover that in one of the later chapters. I'm just thinking of covering it in a slightly different topic. Okay, but this will be covered eventually. But even without this, you can still solve it. What is Fibonacci? We have seen Fibonacci series, right? We have also seen this when we studied recursion itself. What is the recurrence relation for Fibonacci? For P is Fibonacci. Which of them is true? Tn is Tn minus 1 plus Tn minus 2. That's what it is, right? This is the recurrence relation for Fibonacci. So P4, right? So P4 is here, P4 is here. So it can't be this, it can't be this. What about merge sort? So for Q, what is the option? Merge sort is Tn is equal to 2Tn by 2 plus Cn. This is for solving the n by 2 problems. This is for performing the merge, right? For Q, the option is 3, right? Obviously, this is the answer, right? Because Q, it's written as 2. Q is not 2, so this can't be the answer. You're left with only one choice. Okay, but anyway, let's see. For R, which is Quicksort. For Quicksort, what is the algorithm that we have? For Quicksort, you have this. You have this. Tn is Tn minus k plus Tk plus Cn. Because you're breaking an array of size n into 2 arrays of size n minus k and size k, right? And to perform the whole partitioning, you require order of n time. So for R, it will be 1. There is one more towers of Hanoi. For towers of Hanoi, it will be 2. And we'll see towers of Hanoi later. But even without that, you could have solved this problem very easily. Okay, that's why I think our team has set this question. Okay, sounds good. So let's go to the 7th question. Naveen, any questions? Okay, good, good. If there is any question, do let us know in the chat section. I'll stop and go back. Okay, so just give me a second of water break. Let's read this question. Suppose we are sorting an array of 10 integers using some quadratic sorting algorithm. After 4 iterations of the main loop, the array is ordered as this. Okay, 1 2 3 4 5 0 6 7 8. Okay, which statement is correct? Okay, if you're using selection sort, picks the largest items first. Okay, fine. You can implement selection sort in different ways. Okay, let's see this option. The algorithm might be selection sort or insertion sort. Is that true? In selection sort, what happens? I finished 4 iterations, right? In selection sort, at the end of 4 iterations, what should you get? You should get the first 4 elements, 4 smallest elements here. Or if you are using selection sort, which picks the largest elements first, the first 4 largest elements are also here. Okay, because you can write selection sort the way you want. You can either pick the first 4 smallest elements in first 4 iterations, or you can pick the largest 4. Here it's given that our selection sort picks the largest items first. So yes, at the end of 4 iterations, your largest 4 items are here in their actual position, because all these items are less than these 4 items. So it could have been selection sort. Could it be insertion sort? Let's see. Could it be insertion sort? In insertion sort, at the end of 4 iterations, what should happen? Because this is trivially sorted. At the end of first iteration, my second element should be, this should be sorted. At the end of third iteration, first 3 elements. At the end of second iteration. So at the end of fourth iteration, first 5 elements should be sorted. Right? That's all. That's all is the trick, right? Now, in the next iteration, I'll try to place 0 in its original place, right? In insertion sort. At the end of 4 iterations, my first 5 elements should be sorted, right? We learned this when we learned insertion sort, right? That's the loop invariant that we learned, if you recall. Are you also, because we use the CLRS terminology to learn, this is called the loop invariant. At iteration n, your first n-1 elements are already sorted, right? That's what we used when we learned insertion sort. So both options, it could have been either selection sort or insertion sort. So option A is the right option here. Okay. So again, very straightforward problem, easy problem also, I would say. Okay. So the next question here is, you have an array of n elements. Suppose you implement quicksort. Okay, you have an array of n elements. Quicksort by choosing the central element of the array. Here, I have some concern with the word central. Does the central means the middle element in the array, or does it mean the median element in the array? Okay, there is that confusion. Okay, but I'm assuming, because the word central, because if you're a statistician, okay, if you come from machine learning background like me, you would say central means median, right? But of course, it's also, I think this question was framed because I got it clarified. Here it means middle element, not the median element. So I think it would have been better if instead of using the word central, middle was used, but that's okay. Okay. So by always choosing the middle element of the array as the pivot, then the tightest upper bound for the worst case performance. See, whether I choose the first element, look at this. If I'm performing quicksort here, whether I choose the first element or the last element or the middle element, as long as it is not randomized, right? As long as it is not randomized, my worst case performance is going to be order of n square or theta of n square. Let's look at simple example, right? Imagine if all my elements are 5s. Okay, this is like an extreme case. Imagine if all the elements are 5s. Whatever is the middle element, I could pick this middle element, right? My time complexity for this is going to be theta of n square. You do whatever you want. Okay, so whether, as long as we are deterministically, the keyword here is deterministically. Okay, so as long as we are deterministically picking one element always, either the first element, the middle element, second element, kth element, any element. If you're picking one element every time and not randomizing it, okay, your worst case performance is going to be order of n square, because the element you pick could always result in a skewed thing where, so it could always result in a setting where your time taken to solve n is time taken to solve n-1 plus theta of n, right? You could get this extreme situation, right? You could always get this extreme situation in the case of a quicksort. So So the answer here is big O n square, right? It is not big O n log n or theta n log n, primarily because we are not randomizing it. Only in the case of randomization we can guarantee these, right? That too in a probabilistic sense. Okay. So this is an interesting question. So let's go into this. We have solved a very similar question to this in one of the solved problems. Like, I was actually confused whether I already solved this problem or not. So let Tn be a function defined by the recurrence. Okay, this is the recurrence relation. Okay, very good. Which of the following statements is true? The moment you see this, right, first thing you should realize is it's in the form of extended master's theorem, right? This is in the form of extended master's theorem, right? I mean, we have seen extended master's theorem and also problems we have solved. We've actually solved a problem very similar to this, right? What do we have? We have Tn equals to 2t n by 2, right, plus n power half. Okay, so first thing you should realize is in the case of extended master's theorem, what do we have? We have Tn equals to atn by b. Okay, I'm just writing it down here, plus n power k log n power p. Okay, so what are a equals to 2, b equals to 2, okay, k equals to half, okay, k equals to half, p equals to 0, because there is no log term here, right? So just like in the way we have discussed extensively in the course videos and also examples, for extended master's theorem, what do we check? We check whether a is greater than b power k or not. And what is a? A is 2. What is b power k? B is 2. What is k? K is half. Okay, k is half. So obviously 2 is greater than or equal to square root of 2. So this will be case 1 of extended master's theorem. In case 1, what do we have? Very simple. In case 1, what do we have? Again, you have to remember extended master's theorem to solve these problems faster. Otherwise, it will be quite tedious to solve this problem step by step, right? So what will it be? Tn equals to theta of n power log a base b. Log a base b, yes, right? Which is theta of n power log a. A is 2, b is 2. Log 2 base 2 is 1. So it is theta of n power 1. So the answer here is this. So if you know extended master's theorem and if you know this form, right? If you can recall extended master's theorem, solving these slightly tricky cases is going to be super fast, right? So there is certainly value in this. And my suggestion is, if you solve enough practice problems using extended master's theorem, you'll remember it by heart. Okay, actually, I forgot before doing some of these course videos, because I studied extended master's theorem many years back. But by just solving this, by just writing it down multiple times, explaining it to students in videos, and also by solving a few problems, I almost remember it by heart now. Okay, so simple and straightforward. Practice. That's the key here. I can't emphasize that enough. Okay, I think this question is already solved by us, if I'm not wrong. So, okay, there are some problems that we have already solved, right? So, yes.
From one of the, can you solve problem 9 using recurrence tree?
Using recurrence tree. Okay, let's try it. I haven't solved it, but let's try it. Okay, if I can't solve it here, I'll solve it and post the solution later. Okay, I'll try it. Okay, you have a problem of size n, which is broken down into, let me try it. Okay, we have a problem of size n, which is broken down into two problems of size n by 2. And you have theta of, square root of n here. Okay, so this becomes n by 4. This becomes n by 4. Okay, so actually solving this problem using recurrence tree is actually equivalent to almost proving extended master's theorem, which will be quite time taking, but I'll try. I'll see if there is a shortcut, or else I'll prove it more rigorously and send it to you later. But let's try it. So here you have square root of n. Here, what do you have? You have 2 into square root of n by 2, right? So this will now be broken down into n by 8, right? So on and so forth. What will that turn out to be? You will have 4 n by 8. So you have 2 square. You have 4 n by 8s, right? And this will be n by 2 square. Okay, so on and so forth. It will go on up to 1. So what will happen here? So let's write down the recurrence. Let's write down this term that we have. We have square root of n plus 2 into square root of n by 2 power 1, right? This is the second term. What is the third term we have? We have 2 square into square root of n by 2 square, right? Plus, what will the next term be? Next term look like it will be 2 power 4 into square root of n by 2 power 4. Is that what it will be? Let's say n by 16s. I'm just looking it up. Just give me a second, folks. Okay. This will be n by 16s, right? So if I solve all of this, what will it be? If I solve all of this, it will be, how many problems do I have? I have 4 problems here, right? I have 4 problems here. 1, 2, 3, 4. This will become 8 problems here. Oh, so this will be 2 by 3. Okay, sorry. So this will be, okay, let me correct it. It will be 2 power 3 into square root of n by 2 power 3, right? So on and so forth. Okay, till the time. So let's assume the depth of this tree is log n. Let's say k. Let's say k, just for simplicity, right? So then what would this turn out to be? So on and so forth, 2 power k into square root of n by 2 power k. So obviously, n by, because k is this, so this is the recurrence relation that we would get. Okay, now let's try to solve this. Okay, this is going to be fun. Okay, let's try. I mean, I haven't solved it myself, but extended master's theorem is the easier way to solve it. But good, let's try it. Okay, so if I start solving this, what would this look like? This term here is basically 2 power k into 1. So this is 1, because what does this mean? This means 2 power k equals to n, right? So this is 1, this is n. So what is the last term we have? Let's write down last term to first term. Okay, so what is this? First term is 2 power 0 into square root of n by 2 power 0 plus, okay, 2 power 1 into square root of n by 2 power 1 plus 2 power 2 into square root of this plus 2 power 3 into square root of n by 2 power 3, so on and so forth, up to n, right? Up to n, right? This is obviously there is already n here. So it can't be this and it can't be this. It has to be one of these two. Now we have to prove that this is equal to theta of n, because we already saw from master theorem, from extended master theorem, that is theta of n. So now let's try to see. Okay, so let's write down the term right before this. Okay, so we know that this term, right? So how many such terms are here? We have k plus 1 terms here, right? Because this is corresponding to 2 power 0. So we have k plus 1 terms here, right? And k itself is log n. Okay, so I think I need to find some mathematical approximation to solve it now. Let me see. If I take out square root of n outside this, okay, let me see. If I remove square root of n outside of this whole thing, what do I have? I have 2 power 0 by square root of 1, the first term. What is the second term? 2 by square root of 2. What is the third term? 4 by 2 square by square root of 2 square. Plus, I think I'm going somewhere with this. The third term is 2 by 3 by, okay, 2 by 3, 2 power 3 by square root of 2 power 3, so on and so forth. So on and so forth up to 2 power k by square root of 2 power k. Okay, so let's see this. Let me simplify this further. I think this is taking a lot of time, but let's be patient with it. I think we are making some progress. So we have square root of n here. What do we have here? We have 1 plus square root of 2 plus, what is this? This is square root of 4, right? This is square root of 4, this is 4. So this is square root of 2 square plus square root of 2 cube. Just let me know if I've made some mistake here while I'm solving it, right? Because I've not solved it earlier. Okay, so this is what I have. Is there, okay, so how do I solve this stuff? 2 power k, square roots I have, okay? So if I take root 2 also here out, okay? Just give me a second, let me just try to solve this, right? So, okay, I have this. Now I have to prove that this is equal to square root n, right? I have to prove that this is theta of square root n. Okay, how do I prove that? Okay, let me see. So this is square root of 2 Is this some geometric progression? I think this is some geometric progression, right? Okay, let me see. Okay, we have reached till here. Let me see. I'm still struggling with it. Give me a couple of minutes. I'll try to solve it. If I can't, I'll solve it in the spare time, just in the interest of time, and get back to you. So I have square root of n, 1 plus square root of 2 plus square root of 2 square plus square root of 2 cube, plus square root of 2 cube plus square root of 2 power 4, so on and so forth, plus square root of 2 power k. This we know is anyway square root n, right? We know that this is square root n. Now, how do we prove that this whole thing? Okay, so I'm stuck here. I don't know if I can use some, okay, let's write this. This is 2 power half, right? What is the next one? The next one is 2. What is the third one? 2 power 3 by 2. What is the next one? Okay. So let's write it this way then. Okay. Again, I'm still trying to find a solution here. So I have square root of n here. I have 1 plus 2 power half plus 2 plus 2 power 3 by 2 plus 2 power 4 by 2, which is 2, right? So this is nothing but 2, right? 2 power 2, so on and so forth up to 2 power k by 2, right? So if you think about it, this is a geometric progression, right? I'm multiplying everything. I'm multiplying everything with 2 power square root of 2. My first term is 1. My second term is square root 2. My third term is square root 2 multiplied by square root 2, right? So on and so forth. So this is a geometric progression. This is a geometric progression, except that the tricky part here is your multiplier is not. So in geometric progression, you have AR square, AR cube, etc. But here your R is not less than equal to 1. Your R is square root 2. Okay, so this is actually a GP. Okay, this is a geometric progression. This whole thing is a geometric progression. So let's Google search for geometric progression, because I don't remember the formula at the back of my head. Just give me a second. Okay, so anyway, let's try to Google search. Yeah. So I think if you solve this, okay, you can solve it using, let me try it. Let me just Google search for it, because I don't remember the formula by heart. Just give me a second. Geometric progression Wikipedia. Okay, so let's see. Geometric progression sum. Derivation related formula, infinite geometric series. Okay, here you have all of this. Very good. Where is the formula for sum? Okay, here what do we have? Ding, ding, ding. Okay, so this is the formula, but is R should be, to derive the formula, we first write the general geometric series. Okay. Okay. What is the formula that we have now? The formula that we have now is, okay, so it will be slightly different from this. Oh, I think this is the formula. If k equals to 1, when r equals to 1, where is the case where r is greater than 1? I'm looking for that case. We'll have it somewhere. I remember seeing this. Okay, just give me a second, because I don't remember this formula at the top of my head. I Google search whenever I forget them. I think the formula is going to be very similar to this. I think the formula is like this. It will be a r power n minus 1 by r minus 1 when r is greater than 1. I think it will be of this form instead of this form. I think it will be somewhat like this, right? If it is like this, then I think we have a solution, right? Because we only care about so let's look at what we have here. What we have here is this, right? So sorry, just give me a second. What we have is this with a equals to 1, right? A equals to 1, r equals to square root 2, and n equals to k, right? This is what we have. So if I just use this other formula, what will it be? Okay, a into a is 1 anyway. A into r power n. What is r? R is square root of 2. Square root of 2 power n. What is n? N is k, right? K minus 1 by r. So minus 1. Sorry. So minus 1 by, what do I have here? R minus 1. r minus 1 is square root of 2 minus 1. Okay, this is the summation from geometric series. And if you think about it, what is this? If you look at this, what is this? This is nothing but, so this whole expression that we got, this is same as the sum. This is same as this sum. So let me just erase some of this. Okay, I think we got the answer. We convert it into geometric series. Okay, I think that's where it all boils down to. So this geometric series is this. And what is this? This is nothing but 2 power k by 2. And what is 2 power k? 2 power k is n, right? So this is n power half. N power half is square root n. We have square root n here and we have square root n here. So you multiply both of them, you got theta of n. Good job, guys. Okay. You actually, I should have solved this way also earlier, but it was fun solving it. Yeah, see, it took us almost like 10 minutes, right? So Master's theorem is obviously, and of course, I forgot the formula for sum of GP. Come on, I'm very, very bad at remembering formulas. That's why I try to always, of course, for some exams I have to do it. But yeah, thanks for asking this question. Who asked this? Arnab, thank you for asking this question. It was a good exercise, mental exercise, because solving in live is much harder than solving on a notebook, trust me. Okay, so where were we? Okay, so this question, 10th question, right? So yeah, so I think we'll pack it up by 8:30. I'll go slightly fast, do stop me. So there are some questions which, because we had some new team members who joined us. This question I think is already solved in the solved problems, if I'm not wrong. This is already there in the solved problems videos. So there are I think 3-4 problems that are there in this test as well as in the solved problems, right? So I think this is already solved because I remember solving this problem myself. If I'm not wrong, again we can solve it again, but the video is already there in the course videos, so I'm planning to skip it here, right? So just go back to the course videos, and if you cannot find it, do let me know. We will point you to the source. Okay. So there is a small gap because different people were setting up the practice problems and the solved problems. So we had a small gap there. Okay, we'll avoid this in the future anyway. So let's look at this question. This is actually a very interesting question. I'll just take a water break, 10 seconds. Okay, sounds good. The 11th question here is let S be a sorted array. Okay, let S be a sorted array of n integers. Very good. 1, 2, so on and so forth, n integers, sorted array. Tn be the time taken for the most efficient algorithm to determine if there are 2 elements with sum less than 1000 in S. Oh, this is good. Okay, are there 2 elements AI and AJ such that their sum is less than equal to 1000? Let's assume this array is each of these elements is A1, A2 up to AN. Which of the following statements is true? Now let's assume this is an ascending order. Okay, of course you can make it work because nothing is mentioned. Whenever somebody says sorted, we by default assume it is in ascending order, right? So how can we solve this problem? This is actually straightforward, right? If you sum up the first 2 elements and if you sum up the last 2 elements, okay, the maximum sum of any pair of elements, because these 2 are the largest elements, right? If you sum up the last 2 elements, assuming that this is an ascending order, what you get here is the maximum sum possible between any pair of points. If you sum up this, you'll get minimum sum, right? If your 1000 is less than the max sum, there are obviously 2 numbers here whose sum is less than 1000, right? Very simple, because taken any pair of numbers AI and AJ, their sum will lie between min sum and max sum, where min sum is the sum of the first 2 elements, max sum is the sum of the last 2 elements, assuming that this array is sorted. Now, if your 1000 lies between these 2, right? So, but you don't want exactly 1000. You want their sum to be less than 1000. So take the last 2 elements, you get the max sum. If the max sum, right, is greater than 1000, obviously there must be 2 numbers here, which if I sum up, right, you will get a sum which is less than 1000. So I can actually solve this problem in big O1. I don't have to do any complex algorithm for this. This is straightforward staring at us, right? So this is 11th problem. Again, 12th problem is something that we have already sorted because I remember these very well. We have a solved problem in the course videos. We have a solved problem where we exactly solve this problem, right? I think I remember the answer also. I think the answer is this. Again, I think the answer is it's k. Yeah, I think the answer is theta of n log n. Again, this is a repetition. We already have this both in practice problems and in solved problems. So please go back to the course videos where you will find the solution to this. Just in the interest of time. Okay, there's no point repeating the same question here. Okay, so 13th question. Okay, this is interesting. Very similar problem is also there in practice problems, but not the exact problem, I think. So what is the worst case sorting time for bubble sort, merge sort, and quicksort? We know this, right? For bubble sort, it is theta of n square. Merge sort, okay, I think this is the answer. Theta of n square for bubble sort. For merge sort, n log n. Quicksort, theta of n square. So answer is D. This is like a straightforward 1-mark question that is sometimes asked in GATE. Very simple, straightforward question. You can answer it in like 10-15 seconds. Okay, here is a good question. It took me a while to actually solve this problem. But one of our teammates actually gave me a very interesting solution. I'll tell you both solutions, okay? So when n equals to 2 power 2k for some k greater than 0, the recurrence relation equally evaluates to what? So here he is not asking big O or theta or omega. He's saying if you solve this recurrence relation, what do you exactly get? Because if you look at this, most of them are very similar. Between this and this, there is only +1 difference, right? So the shortcut to solve this problem, there is a shortcut and there is a lengthier way. Okay, the shortcut to solve this problem is take T2. What is T2? T2 is square root of 2 into T2 by 2, which is T1. Right? T1, oh sorry, square root of, sorry, let me write it down carefully. Okay, so square root of 2, Tn by 2. So T1 is 1, we know that, plus square root of n. This is 2 root 2, right? This is what it is, right? Because T1 equals to 1. Okay, so this is T2. Now, which of these 4 actually evaluate to 2 root 2? This is like eliminating options. What is this? This is square root of n, which is root 2. Root 2 into, what is log n? Log 2 base 2 is 1. 1 plus 1 is 2. So this could be an answer. What about this? This is root n, which is square root 2. Log 2 base 2 is 1. So this can't be an answer. What about this? This is square root of 2, right? Square root of 2 into log of square root of 2. Now this is not equal to 2 root 2. Sorry? First option is the right option. But I'm just checking if other options are also possible, no? I have to check for all options. Because there could be multiple options, then I need to be careful. Right? That's okay. Okay. So here you have 2 into log root 2. This is not equal to 2 root 2. So you've eliminated all these 3 options. There is only one option left. So that's one strategy of solving it. It's very fast. Okay. So one of our teammates actually told us this solution. It's a very simple, elegant solution. I didn't think of this, by the way. I actually started solving because I don't look at the solution. I don't look at the options. I start solving them first. Okay. Let's look at the detailed solution for this. Of course, it's slightly lengthy, but we can do it. Okay. Remember this, and you have k greater than equal to 0. Let's solve the whole thing, right? So you have Tn equals to root 2 Tn by 2 plus square root of n, right? Now I can break this up again into square root of 2 into Tn by 2. What is Tn by 2 now? Root 2 into Tn by 4, right? Plus root n by 2, right? Plus square root of n. Basically, I'm substituting everything here, right? I'm basically substituting the value of Tn by 2 into this, right? If I keep doing it, what do I get? Let's expand on this. I'll get square root of 2, right? So I can take square root of 2 outside here, okay? Because I want to get some neat terms. Square root of 2 square, Tn by 4, right? Or Tn, instead of writing 4, I can write it as n by 2 square, okay? Tn by 2 square plus root 2 into root n by 2 power 1 plus root n. This root n here, root 2 into this 2 multiplication got us here, right? Now, if I expand on this, I would get root 2 power 3. If I replace this again further, I would get Tn by 2 power 3. I'm just expanding on this plus, of course, when I expand this, I get 2 terms, right? I get root 2 squared square root of n by 2 square plus square root of 2 n by 2 power 1 plus square root of n, and so on and so forth. Okay, you'll get this. So now if you simplify this, if you keep simplifying this up to n, if you expand up to n, this is if you let's say, what do we have? We have n equals to 2 power 2k, right? We have n equals to 2 power 2k, right? So what is log n? Log n is 2k. Now, if I keep expanding this, the final term that I'll get here, will look like this. The final term, of course, you can go step by step and get this also. What you'll get here is, it's a slightly cumbersome term, bear with me, root 2 power log n, right, t1 plus root n plus root 2 power 1, right, root n by 2 power 1. Again, I'm just doing what we had. Basically, I'm rearranging all of this. If I keep expanding this, finally I'll get t1, right, plus root 2 square n by 2 power 2, so on and so forth, up to root 2 log n into 1. Seems like a crazy thing, right? But one thing that we can use here is, we know that n equals to 2 power 2k. Now, if I use this in this expression, what happens to this whole expression, right? Look at this. So this becomes root 2 power 2k. Look at what happens to this. This becomes root 2 power 2k. What is log n? Log n is 2k. Okay, this becomes this, right? T1 is anyway 1, so I can ignore this. Plus, what is root n? Right? Look at what is root n. Root n is, so if n is this, what is square root of n? Square root of n is 2 power k. Right? Square root of this. So this multiplied by half is 2 power k. Right? So from here I get 2 power k. From here. What about the second term? I get square root of 2 into square root of n by 2 power 1. Right? If you notice, these two will cancel out again. I'm left with square root of n. What is square root of n again? Nothing but 2 power k. Right? I'm again left with 2 power k. What is this? This is also 2 power k, because I can remove the square root and multiply this by half, and I get 2 power k here. So what am I getting? I'm getting only 2 power k's every time. So I got 2 power k. I got 1 2 power k from here. For each of these terms, I'm getting a 2 power k. So here also you can delete these two and you get square root of n. Square root of n is again 2 power k. Right? So on and so forth. How many such terms do you get? See, here you have 2 power 0, 2 power 1, so on and so forth, right? So what is the total number of terms that you will get? The total number of terms that you will get here is 2 power k, right? 2 power k is nothing but square root n. You will get log n plus 1 terms. Okay, you can actually work this out carefully. You'll get log n plus 1 terms, right? And what is 2 power k? 2 power k is square root of n. Is nothing but square root of n. This is one of the options that we have. Of course, this is a much more lengthy. I've skipped some of the steps here, because otherwise it will take us like 15-20 minutes to solve it. Okay, but if you just fill these steps in carefully, you will get to this notation. Keep canceling it out. It took me like, it's literally on my notebook, it's 1 page of detailed proof. Okay, but these are the steps, and this would take a lot of time. In an examination setting, this would take a lot of time, and the substitution method and elimination is a much faster method. Unfortunately so, but it's important for us to learn the genuine technique also. But in an examination setting, this could take you 10 minutes, right? Or even more sometimes. Okay. So for a 2-mark question in GATE, for a 2-mark question, you should allocate roughly about 4 minutes. For a 1-mark question, you should roughly allocate 2 minutes. This is like a very good time allocation. A problem like this may be maybe a 2-mark question, but you're allocating 10 minutes. That means you're compromising on the time interval that you have. So sometimes in examinations, elimination is a good strategy. Okay. So, but it's good to know the other ways of solving it also. Okay. So if any of you face this problem where the keyboard is, where the keypad is overlapping, just do one thing. Just click elsewhere on the screen. The keypad will vanish. Just click again here. Your keypad will be available, right? Oh, this is a very interesting question again. I enjoyed solving this question. So you have Fibonacci of n. If n equals to 0, then return 1. Else, if n equals to 1, return 1. Else, Fibonacci of n minus 1 plus Fibonacci of n minus 2. The question here is the number of times Fibonacci is called, including the first call for the evaluation. So let's see. This is a very good question, actually. Of course, it's straightforward. It's not rocket science. So let's assume Fibonacci of 0. How many times you'll call this function? Once. Right? You have to call once. Fibonacci of 1, because it returns 1 again. Okay, so once. For Fibonacci of 2, what do you have to call? You're calling Fibonacci of 2 as a function once. You're calling this once, right? Plus, you have to call Fibonacci of 1 and Fibonacci of 2, right? These two require one call and one call. So this requires one call here, and this requires one call here. This call is the Fibonacci of 2 call. So total calls required are 3. Similarly, for Fibonacci of 3, one call for calling the Fibonacci of 3 plus one call for Fibonacci of 2. But to solve Fibonacci of 2, I need 3 calls, right? For solving Fibonacci of 1, I need one call, right? So total calls is 5. Now, what about Fibonacci of 4? To call Fibonacci of 4 while calling F4, I'm just calling it F instead of Fibonacci, okay? So F4, one call for F4 itself. Then how many calls for F3? To solve F3, I need 5 calls, right? To solve F2, I need 3 more calls. So what is this equivalent to? 5, 3, 8 plus 1, 9. Similarly, for F5, 1 plus 9 plus 5. 1 plus 9 plus 5. This is 15. What about F6? 1 plus 15 plus 9, right? 15 plus 9. This is 25. What about F7? The question here is about F7, right? Or Fibonacci 7. Once for Fibonacci itself to call the Fibonacci, including the first call, 25 for Fibonacci 6, 15 for Fibonacci 5. So this is 41. So the answer here is 41. You can just fill it here as 41 if you click on it, right? So this is a fill in the blank. It's an interesting question, testing your knowledge of recurrence relations and how recurrences work, right? So now let's go to the next question, which is consider the recursive sorting algorithm. Sorry, recursive quicksort algorithm with random pivoting. Very good. I like this. So you're picking the pivot element randomly. That's called the randomized quicksort. That is, in each recursive call, a pivot is chosen uniformly at random from the subarray being sorted. We know the definition. We learned it in the course also. When this randomized algorithm is applied to any array of size n, all whose elements are distinct. This is important. All the elements are distinct. What is the probability that the smallest and the largest element in the array are compared during the run of the algorithm? Very good question, actually. So how does quicksort work? Okay, suppose I pick a point as a pivot. Okay, I compare this pivot with all other elements. Basically, what am I doing? If I pick up a pivot element, I compare this with pivot, right? I compare all the elements with pivot except the pivot element itself, and readjust such that all the elements less than equal to pivot are on this side and greater than equal to pivot are on this side. That's what I'm trying to achieve, right? Which means the pivot element is what is being compared with all other elements. What is the question here? What is the probability that the smallest and the largest elements are compared during the run of the algorithm? Okay. So now, if your pivot element is the smallest element, if your pivot element is the smallest element, right? Or if your pivot element is the largest element, it is possible, right? Because you're picking pivot element randomly, it could be the smallest element or the largest element, right? When you pick your pivot element as the smallest element or the largest element, then it will be compared during the run of the algorithm, right? So you're given n numbers and all these numbers are distinct. That's important. For n distinct numbers, there is one minimal number, one smallest number, and one largest number, right? And what is the probability of picking a smallest number or a largest number given n numbers? It is 2 by n. This is the probability of picking the smallest number or the largest number given that all the numbers are distinct. Now, when you pick the smallest element or the largest element as pivot, that would be compared against all other numbers, right? That's what happens in quicksort, right? So the probability of this being satisfied is equivalent to probability of picking the smallest element or the largest element. And that probability is trivially 2 by n. It's actually a very simple problem, but written very intricately and written very carefully, right? So that it looks like a technically hard problem, right? Straightforward problem. Okay. So I think we have solved a similar problem also in the course videos, if I'm not wrong. Yeah, I think we solved a similar problem. Yeah. Yeah. Oh, there is a question very similar to this question. Okay, good. Okay. Okay. So there is actually a GATE 2019 question. There is a GATE 2019 question, this year GATE, which happened in February of 2019, which is very similar to this. I think that question is also there in the practice questions, if I'm not wrong. Okay. So let's go to the 17th question, which is, suppose we are sorting an array of 8 integers using some quadratic sorting algorithm. After 4 iterations of the algorithm's main loop, the array elements are ordered like this. Okay. Which of the statement is correct? Okay. So let's see. So we have two algorithms, selection sort and insertion sort. Okay. Can this be insertion sort? It says selection sort picks the largest items first. Largest items, which means at the end of 4 iterations, 4 largest elements should be here, which is not the case. So it cannot be selection sort. Can it be insertion sort? Let's see. Insertion sort, at the end of 4 iterations, the first 5 elements should be sorted. Oh, it is sorted. The first 5 elements are already sorted, 2, 4, 5, 7, 8. So this can be insertion sort, but not selection sort. So where is that option? It's not selection sort, but it could be insertion sort. So option 3 is the right option here, right? Again, this is very similar to the other problem that we solved a little earlier. Okay. Oh, this is the problem. I think this is the 2019 GATE problem. Yes. So this is there. This is also there in the solved problems. Again, this is a repetition here. This is actually a solved problem with some numbers here. Instead of n and 2, etc., here they say, I'm given 25 integers, right? Assume that it is chosen randomly. What is the worst possible location of the first? So we have already solved this in the solved problems. I remember the answer also. I think it is 0.08. Okay, so just go back to the course videos. Sorry for the repetition here. We'll avoid these in the future, but a couple of problems have been repeated. Okay, so let's go to the 19th question. Okay, this is a good question actually. Okay, this was slightly a mind twister, tricky question. Okay, so the number of comparisons required to find the minimum and maximum of 100 numbers. Okay, very good. Suppose I'm given 100 numbers, A1, A2, so on, so forth. Let's say A3, A4. Let's write down a few numbers, right? Up to A100. I want to find the min and max. First thing, what do? I pick the first 2 numbers, whichever is the smaller. So I compare first number and second number. Let's say A1 is smaller than A2. So I'll make min equals to A1, right? If A1 is less than A2, okay? And I'll say max equals, initially, I initialize these here. So I have done one comparison here. I've done one comparison already. Now the trick here, because the question here is the minimum number of comparisons. The question here is minimum number of comparisons. I've already done one comparison. Now what I'll do here is I'll pick three numbers. I'll pick A3, A4, A5. I'll pick 3 numbers, A3, A4, A5. What I'll do now is, sorry, no, instead of picking 3 numbers, let's pick 2 numbers. I think 3 numbers won't work. Okay, so sorry. Let's pick 2 numbers now. Instead of picking 1 number each time, let's pick 2 numbers. Okay, first I'll compare these 2. Let's say A3 is greater than A4. Okay, let's assume A3 is greater than A4, right? Then what do I need to do? Then A3 can be maximum, A3 can never be minimum, right? Because A3 is greater than A4, right? So what will I do? I'll compare A3 with my max now. So first I've picked 2 elements, I've done one comparison. Then for the next 2 elements, there is one comparison here. The other comparison is compare A3 versus max. I don't have to compare A3 with minimum because A3 can never be minimum, right? Because A4 is lesser than that. So next I'll compare A4 and minimum. If A4 is less than minimum, I'll make minimum equals to A4. If A3 is greater than max, I'll make A3 equals to, so I'll come this, and this. So for these 2 numbers, I have made 3 comparisons, right? For 2 numbers, I have made 3 comparisons. Next, I'll take 2 more numbers, right? Next, I'll make 2 more numbers, right? So for 4 numbers, how many comparisons do I need? I will need 6 comparisons. Now, how many numbers I have here? Because first 2 numbers have already been processed. I have 98 numbers, sorry. sorry, I have 98 numbers, right? If I have 98 numbers, how many comparisons do I have to do? 98 into 3 by 2. This is 49. 49 threes are 147. Okay, here you might be confused and you might write the answer as 147. It's not, because there is this first comparison also. To initialize your min and max, there is one comparison here. So 147 plus 1, 148 is the right answer. Okay, that's the right answer. Actually, it's very confusing. Many people will just say, oh, I have 98 numbers. Or sometimes people also could say, oh, 2, 3, 4, 6, 100, how much? Okay, so you have to remember that you're initializing min and max by performing the comparison between A1 and A2. So you only have to worry about the rest of the 98 numbers, right? So 148 is the right answer here. So yeah, these are the questions for today. And thanks for making this fun, especially solving that harder geometric progression problem. I was not sure I could solve it in a limited period of time. I was really not sure. I thought I might have to take it offline and solve it carefully after this session. But thankfully, we got it into a geometric progression. See, at the end of the day, what we did with what I think Anirban asked. His name was Anirban, right? I forgot. Arnab, sorry. Yeah. So what Arnab asked was actually, we are literally proving extended master's theorem there, or at least a part of the extended master's theorem, because we didn't have the log term there. But if you can actually prove extended master's theorem. It's not rocket science. If you're careful with the math, you can go ahead and solve it carefully, right? It was fun working it out, and thank you for joining us today. As always, our pleasure. And we would have the next live session on Saturday, as usual, 7 to 8:30 p.m. To all the registered students, we are giving a little leeway here and a buffer time.
Just from them, please solve question number 4.
Question number 4. What is question number 4? Just a second. Did we not solve it? Just give me a second.
I've solved it, but
We still have a doubt.
Oh, is it? Okay. So question number 4. Let me just go there. Just give me a second. Question number 4 here, right? Okay, this question was straightforward. Okay, let me show you. So you have a sequence of 8 distinct integers in a sorted array, right? I think I already have this. Let me just open up the slide the notes that I have written here. Just give me a sec so that we can write on top of it, right? On top of it itself. Yes, this is what it is, right? This is a good thing with the tool, with this brilliant tool that we use. I really love this because I can always go back. So sequence of 8 distinct integers in ascending order. How many distinct pairs of sequences B and C are there which satisfy these 3 conditions? The first condition is each is sorted in ascending order. So B and C need to be in sorted orders, right? That's important. Next, B has 5 elements and C has 3 elements. The result of merging B and C gives A. What does this mean? This means every element of A should be present either in B or in C. It cannot, so B union C should be A and B intersection C should be null set, right? Because every element here should be present in B or C at least once and only once, not at least exactly once. So what does this equal? What is this equivalent to? It is equivalent to, suppose if I pick 3 numbers here, if I pick A2, A6 and A8, let's assume I pick these 3 numbers. Some 3 random numbers I pick. Let's assume I pick, how many ways can I pick 3 random numbers from this? 8C3, 8 choose 3, right? Suppose, let's assume I pick A2, A6 and A8, okay? There is only one way I can place them in array C, because array C got to be sorted and all the numbers are distinct. The only way I can place these 3 numbers in array C is A2, A6 and A8. There is only one way I can place them, right? There are 8C3 ways in which I can choose 3 numbers. But once I pick 3 numbers, there is only one way in which I can place them in array C. So once I've picked up these 3 numbers, there are 5 more numbers. And those 5 numbers also need to be placed. Let's assume I place A1 here. A2 is already here. So I can place A3 here, A4 here. Okay, let's assume this is the sorted order. A5 here. I can't place A6. I can place A7 here. And I can't change the order because B and C have to be sorted. By condition 1, B and C have to be sorted. So there is only one way for me to place these items in array B. There is only one way for me to place items in array C. But there are 8 choose 3 ways of picking 3 random elements from array A. Right? So the total number of distinct pairs of sequences is equal to 8C3. And when you solve 8C3, we got 56. Right? Very simple question. This is a basic question in combinatorics. Okay. So, yes.
Sir, if you merge both B and C, will it maintain the same order as C?
Yes, why not? So by merge, I mean, oh, by the way, I think you're confused with the word merge here. This merge is in merge sort ka merge. Okay, so the key thing here is merge doesn't mean B concatenation with C. This is not this merging. This is not merging as in concatenating. It is not. Merging as in merge sorts merging. Merge sort merge, basically if you give two arrays, right? It compares these individual elements, right? And then merges them into a larger array. I think that's what you're confused with, right? It is not concatenation. This is called concatenation. Merge sort ka merge procedure is called merging. Okay, I think that's what you're confused with. Okay, yes. What is the question?
Will we consider space of stack frames while computing space complexity of merge?
We do actually. Okay, good question anyway. So actually you are supposed to, right? So if you take merge sort, what is the time complexity of merge sort? Okay, let's look it up. Okay, merge sort, you create these two temporary arrays called left and right, of sizes n by 2. The maximum size of these two will be n by 2. So the total space is theta of n. What is the total space for the stack? The total space that you have in the stack itself is not more than theta of n. It is just not explained here. When you're discussing merge sort, people often don't talk about the stack space. But if you count the stack space also, stack space is obviously less than theta of n, because you're not making order of n calls, right? You're not making order of n calls, right? So the stack space, even if you count it, anyway you have theta of n, right? You anyway have theta of n here, right? So if you count the stack space here, it is still, because the stack space is less than theta of n, the overall space is anyway going to be theta of n. Your question should be, what happens in Quicksort? This is a big mistake that many people make. For Quicksort, merge sort is still straightforward. The trick part is in Quicksort. For Quicksort, many people think the time complexity is theta of 1, which is not. There are actually multiple ways of implementing it. Okay, actually we have discussed this in the course videos also, right? There is something called as tail recursion. There is something called a tail recursion way of doing it, and the regular non-tail recursion way of doing it. Okay, we have discussed this in the course videos in a lot of detail. So if you do the regular non-tail recursion version, you get theta of n space, worst case. If you do the tail recursion approach, you would get theta of log n. So the tail recursion, I think this algorithm is from 1970s. There is this famous author, right, who wrote a book, Sedgwick, right? I think this is called the Sedgwick's, I think this is Sedgwick's PhD thesis, if I'm not wrong. Again, I'll have to Google search it. The tail recursion way of optimizing Quicksort, because for Quicksort, the regular one takes theta of n space because of your stack in the worst case. There is something called as a Sedgwick's algorithm from 1972. I think it is Sedgwick's PhD thesis, if I'm not wrong, where he showed that there is this tail recursion approach, which is theta of log n. But for merge sort, we already have theta of n. Even if you count your stack will not be deeper than theta of n, right? So your overall space complexity is going to be theta of n. But it's a good question. But the better question is about Quicksort. Yes?
Do we have stack space for tail recursion?
Yes, we will use stack space. For any recursion, the programming language has to use, you can't skip that. Okay? But tail recursion is optimized. See, we are not saying that for tail recursion, we don't have stack space. We do. Okay? Again, I don't want to go into the depths of tail recursion, how it works here, because we've already explained this in the course videos in a lot of detail. But tail recursion, see, any recursion has to use stack space. You can't run away from that, because that's how your compilers work, right? That's how the program is executed at runtime. You can't escape that fact. But tail recursion optimizes that, right? Tail recursion optimizes it and uses it better, right? So yeah, so that's what it is. Anyway, so just a quick point that I wanted to make. I'll just come to you, Naveen, just a second. Naveen is looking through the chats. Just give me a second. So a key thing is for Saturday, as I was just informing earlier also, we are giving little extension for the students because we had more content to finish in the last 4 days. We wanted to give them a little more time to finish all of the sorting algorithms. all the content that we have, all the assignments or practice problems and solved problems. We'll also be sending out 30 practice problems covering all the concepts that we have done till now. Okay. Sorry, please solve all of them and we'll have a discussion on Saturday evening with all the 30 problems, as many as we can cover in a 1.5 hour session. Whatever we could not cover in the 1.5 sessions, we'll anyway send you written detailed answers. Okay. So, but from next week, let's speed it up. Okay, because we got to speed up to move faster and cover this data structures and algorithms so that we can move to other subjects. I'm not saying let's rush through it. All that I'm saying is let's speed up a little more, because the first week we gave some leeway to students, but let's slowly progress and move faster. Yes, Naveen.
Question 11, all are the same.
What is question 11? Okay, let me go through this. Just a second, share. Okay, I'm screen sharing here. What is question 11? Okay, so what happens if all are same? What is the problem there? Okay, let's assume I have these n numbers, right? My first number, my second number, my nth number, my n minus 1th number. So let's assume all the numbers are same. Let's assume this number is 6, this number is 6. See, what is our goal? Our goal is are there two numbers aj that are less than 1000? What if all the numbers are the same? It doesn't hurt me, right? So the sum here is 12, which means if all the numbers are the same, the min sum, right? The min sum is same as the max sum, right? But I can still answer this question. If these two if all the numbers are 6, let's say 6 plus 6 is 12, which means there are certainly a pair of numbers whose sum is less than 1000. Imagine instead of these numbers being 6s, they're 600s. Okay, then what is my pair sum here? 1200. Right? My pair sum, my min sum is 1200, my max sum is also 1200, which means there cannot be a pair of numbers whose sum is less than 1000. Right? So the system, the solution that we discussed earlier works even if all the numbers are the same. No problems with it. Okay. So I hope this is clear. Okay, folks. Okay. Yeah, we rushed a little fast this time because we had more questions to solve. And we also had some interesting challenge in between. I really loved it. Okay, nice talking to you as usual. Keep practicing. There is nothing that beats practice. Of course, please go. You need to know the foundations. Let's not ignore the basic concepts and foundations in the videos, but practice. That's the key to cracking any gate exam. Forget about any exam. Forget about any gate exam. For any exam, practice is mandatory. Okay. Happy problem solving and see you again on Saturday. Please finish all of the course videos up to end of sorting and solve all the problems. We'll send you 30 practice problems by end of tomorrow, right? Yeah, we'll send you by end of tomorrow. We're just picking up some good questions so that you revise all the concepts you learned, and we'll double down next week faster. See you folks. Have a good evening. Thank you for joining us. Thank you once again.